Yes, quantum is going to be new because you barely touched it in honors chem, but you did touch like what the quantum mechanical model utilizes, which is SPDF, the electron configurations. So technically you do know quantum, it's just not the extent that AP is looking for you to know. And, oh, good, okay. This thing's having a hard time today in general. All right, so basically we know that electrons are the most important subatomic molecule in the world. It's the thing that determines all behavior, so all chemical reactivity, hence why we make ions, we make bonds, we can excite those electrons. Can we see the excitement of an electron?
Yes.
No, we cannot. What can we see?
It's going back down again.
Fine, so we're talking about like a really microscopic level. So no, you cannot see the excitement of an electron to an upper level energy level or a excited state. You can only see the fall, right? You can see the excited state go back down the ground state, not the other way around. Because from that, with respect to that, that's releasing maybe a form of light that we can see, which is the visible spectrum. All right, so the electron is really important, which is why the quantum mechanical model really hits that as the high note. It makes sure that you understand where the electrons are, what they're doing, how the electrons are arranged around the nucleus, etc. And that gives us information about all these properties. You know, properties regarding metals versus nonmetals, what ion charge something would form, why some things are more reactive than others, and then how those reactivity kind of correlate with properties that we know about elements. So the electron rules the world. Got it? Okay. So, what is this electron configuration for? You need a periodic table, probably.
Vanadium.
Vanadium, right? Vanadium. So we have vanadium, and remember with the electron configurations, you have a block system on the periodic table. You always have a periodic table available. I had to memorize the order at which orbitals were filled. Don't know why. That's how my teacher taught me, and I was like, I have no idea what an electron configuration is or how to do it until I started teaching. I was like, aha, this makes it easier. I'm struggling. Okay, so we have a block system. Just gonna leave that right there. And the S block is the, woo! You guys see this? It's not me. Okay, I will fix this in a second. This happens every single day. Okay, S block is over here in group 1 and 2. Helium truly belongs right here on the top of group 2 in terms of electron configuration orbital filling because it's teeny tiny and it does not have p orbitals. P block is over here 3 through 8. D block, when you hit D block, you take the period number, which is 1 through 7, right, as according to the rows. You take the period number and you subtract 1. So we call that n-1 because n is technically the term or the variable that represents energy level, aka period number. And then when you get to F block, you do n-2. F block fits into what part of the periodic table? Yeah, so the lengthened series and actinide series. If you look on that one over there, you can see the color coding. So the first, like light blue, fits into the 6s2, and then when you hit F block, you do 4f14, and then here on D block, you go 5d10, and then 6p6. So basically, when you fit F block into the sixth row, you go 6s2, because that's your 6, that's your cesium and barium, and then you fit the first row of F block in. So tell me what that is again. What fits there? 4, good, because you want to put a 6, but then remember you do n-2, so that's 4f14, because there are 14 electrons or building of electrons across the entirety of F block. And then once you fulfill F block, you go back up to D block, and then what is that going to be? 5d10, because there are 10 electrons across D block. And so if we were, you know, we had a bunch of this stuff before. If I made it all the way to the end of P block, who would I be writing the electron configuration for? 6p6. So who would that be regarding? I'm down here, aren't I? Radon. All right, so that's just horrible to have to write out from the top. 1s2, 2s2, 2p6, 3s2, 3p6, blah, 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 blah. So what we tend to do is we use the noble gas shortcut, which takes into account the last noble gas you passed. Do you remember that?
Yeah.
so it makes life easier. So that's why technically actually why I started here, because who's the noble gas I passed right before 6s? Xenon. So when I put bracket xenon, technically I'm saying 1s2, 2s2, blah 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 till I get to xenon, and in just that bracket, and then I go from that last noble gas and I continue until I get to wherever I'm going. Now, of course, I went to radon, which is its own noble gas, so technically I could have put brackets on itself, which is a cheap, easy way to do it, but normally you don't write electron configurations for noble gases because they are that easy. Okay, let's do another practice. Do bromine. Bromine. Do not do shortcut. Do the full thing. And then we'll write the orbital diagram. I'm just going to fix this board. Get me started, JT.
1s2.
Again.
2s2.
Marcus. Marion. Margaret. Where are we at now? Argon. Okay. Queef.
4s2.
Cassie. Good. So we hit 3D and we did subtract 1. Darcy. Or are we stopping at 5? Because what? That's where bromine is. There's 5 electrons and it's p sublevel. Okay. So before we move on, I know you know how many valence electrons bromine has. How many valence electrons? How do you know 7? Because of the 7th group. So whatever the group number is, 1 through 8, it tells you the number of valence electrons. We know that. How do you identify that here? Be loud and proud, man. No one can hear you.
Look at the last, like the furthest energy level you've been to, just add the electrons together.
So who's the last energy level here? 4, right? So there's 4s2 and 3 or 4 p5. So if you had to circle the valence electrons, it would be 2 and 5 right here. And so that's why when we're looking at achieving octet in the reference of forming ions, that's why bromine is not going to lose 7 electrons, because it's going to pass the 4, which is the break point of are you going to lose electrons or gain electrons. It has 1 extra space left for an additional electron in its p sublevel, which is why it forms bromine 1- when it forms an ion. So that's how we know ion prediction. So like we just memorized, oh, if you're in group 2, you form a what charge? 2 plus charge. But why?
It's easier for it to lose 2.
Because there's 2 valence electrons and it's what? Well, and it's 2s shell, right? So 2s is, or sorry, not 2s. S2 is its subshell. Okay, so that's our electron configuration. If you have an orbital diagram, it's going to look different. It's going to be like a picture. So I'm going to do that for vanadium that we have up here. So vanadium's electron configuration is kind of long, but we're going to write the orbital diagram, which has a series of lines and arrows. So you draw your orbital, which is represented as a line. You call it 1s. 1s. How many electrons are there? 2. 1 spins up, 1 spins down. So we draw arrows to indicate spinning up and spinning down, also known as spinning clockwise and counterclockwise. That's truly the language used, but we just say up and down. The reason they don't spin the same direction is because it creates a magnetic force. So when they spin opposite directions, it's more stable. So 2s2, up, down, 2p6. How many orbitals are in the p sublevel? 3. Okay, so I'm just trying to tell you the vocab. 3 orbitals in the p sublevel, because in p you have p x, which this is the sphere is the shape of the s orbital. A dumbbell is the shape of the p orbital, but a sphere can't take on any other orientation. It's a sphere, right? This can take on other orientations with reference to like x, y, and z axis. So this is like px, this is py, and then out of the board and into the board is pz. So because we have 3 different orientations, the p sub-level has 3 orbitals. So then we draw 3 orbitals, 1, 2, 3. We label them all 2p, and then we fill in the gaps. So because we follow the rules of electron orbital filling, there are 3 rules, which I think is on the next letter down here. What were those 3 rules? Okay, off-Gall's principle, which says what? So start low. What does that mean? Start at 1, go to 2, and then go to 3, right? You're not going to say, I'm going to throw some electrons in 7s, right? You don't get to choose. It's 1, 2, 3. Who's next? Hund's 1's rule, which means we fill 1 electron per orbital, and then if we have to go back and double up, we do, which we're going to have to. We've got to put 6 in this guy, right? And Pauli exclusion, which refers to, it does refer to spin. It actually refers to, there's no, when we start talking about the 4 quantum numbers, there's a single electron has its own code, its own 4-digit code, which is it's representing its Pauli exclusion principle, meaning there's no other, like it's an exclusive set of numbers for one given electron. It's exclusive, like it's only there for one thing. But what we also refer to it as is we can only pair up electrons. We can't put like 4 or 6 in one orbital. It only goes up to 2. So I say Pauli pairs. Okay, so we're filling this up all the way, so I'm going to follow the rules. 1, 1, 1, 2, 2, 2. Keep going. This is 3s, up, down. 3p, you draw all 3. 1, 1, 1, 2, 2, 2. 4s, up, down. And then how many orbitals are in 5? I mean, are in D. 5, great. Sometimes my brain is faster than my mouth. Okay, so, oops. So I'm going to try to make some space here. Perfect. Okay, so we're going to draw all 5. Doesn't matter if you need them or not. You draw all 5 and you label them all 3D. And how many are filled here? Say again? 3 are half filled. I was actually hoping everybody would say 3, and I was going to say no, none of them are filled. They're all there's 3 that are half filled. So good job. So 3D, 1, 1, 1, and then nothing else is filled past that. So vanadium is weird. It's a transition metal. It doesn't have a predicted valence count because it can exchange more than just its true valence electrons. So its truest form of valence electrons are 4s. So it could form a 2+ charge, vanadium 2+. But these are all really, really close in energy level, like our energy. So 4s and 3d are like this in terms of energy. So because you can technically lose anything that's of high energy, you could lose all 5 of these, which is why vanadium can form a 5+, or a 4+, or a 3+. Remember, transition metals, they have variable charges, like copper 2+, copper 1+. It's because of their inner d orbital electrons that they can also lose. So transition metals are somewhat unpredictable because they have the ability to lose more than just their truest of valence shells. Okay. I think we've mainly talked about all this. Moving on, okay? So this is what I'm talking about. This is what I had to memorize. But one thing you should notice is this is All-Falls diagram. All-Falls diagram is showing you the energy levels in order. Who's the lowest energy level? 1, right? So 1 is the lowest. What you should notice is there's a very, very, very large gap in energy level 1 and 2. Okay, so that's significant versus the energy level gap between 2 and 3, 4, 5, 6, and 7. So they start to get crunched up here. And then also you can tell the order in which they are filled because, like, we just did 4s. What comes next? 3D. And so that's what our little trick on the periodic table N-1 is telling us to do, is fill the 3D, not the 4D. So you can see how that kind of wiggles through as you fill different orbitals based on their level of energy they attain, or they contain. And so that's All-Falls diagram, but the big difference is that that first energy level, the second, has a very large gap. And we talked about this. I'm moving on. Okay. So as I kept saying, like, groups 1 through 8, just remember the representative elements are group 1A, 2A, 3 through 8A. These are the B elements, the transition metals. So if we ever say representative elements, it's just normal groups we deal with, 1, 2, 3 through 8. Got it? Yes? Okay. And then eventually you'll have to start explaining why some electron configurations exist as they are. So I just mentioned copper. What 2 forms of copper did we say we know about?
Copper 2, copper 1.
Right, so 1 and 2. So how in the world is copper exchanging a certain number of electrons and why? So what happens is we're looking to make a very stable electron configuration. So we want to limit all electron-electron repulsion. Some orbitals have more space than others. So like you can see S is pretty condensed, but then like D looks like this. It's a double dumbbell. So there's a lot more space to work with. So, and P as well, F as well, so F's even bigger. So what happens is to eliminate some of this electron-electron repulsion, copper and other transition metals can do electron promotion. So they're moving them up to another energy level. So this is the predicted form, yes? Copper stops at 9. So because you have more room in your D block, you can promote one of the S electrons to the D block simply because it has more space. So it's going to help eliminate some of that electron-electron repulsion. So what is the truest, the best electron configuration for copper? 1s2, 2s2, 3p6, 4s1. So that leaves 1 in the s orbital, which is going to have a lot of space to play, and then 3d10. Notice we never changed the number of electrons. There's still how many? 29, right? There's still 29 here. There's still 29 there. It's just we've spread them out to accommodate for electron-electron repulsion. Now, if you're going to form copper 2, it's simply because you're losing those 2 electrons from the 4th energy level, which is the valence shell here. But when you're forming copper 1, what do you think is happening? You're losing this one right here to form the 1 plus charge. So because copper can promote electrons, and it can demote electrons if it wanted to, it could go right back to its 4s shell. That's why it forms 2 different forms of itself, 2 different charges. So we see those irregularities not just in copper, but everything below copper. So who's below copper? Silver, gold, and Rg. Rg. What is?
Well, that's
not one I often discuss.
That's very interesting.
Okay, so it happens with copper, which is going to be the ending of 3d9, and then look for chromium. Where's chromium here? Where does it end? It stops at 3d4, right? So think of that, 3d4. You've got how many orbitals work within D block? How many? 5 orbitals, but there's a total of 10 electrons, right? 2 electrons per orbital. If you have 3d4, what does this look like to you? Orbital diagram style. So not all the way filled at all, so it's only 4 of them are half filled. So you could take one of your S's and plop it into that last unfilled orbital. So what we tend to see experimentally is that we predict these unfilled orbitals stopping at 3d4, 3d9, 4d4, even a 6, and then we have an 8. So notice there's extra space there. So what all of these can do is they can all do electron promotion. And for example, we just talked about the copper one. Chromium's going to throw it for us up to a 3d. Molybdenum's going to put one of its up to its 4d4 to make 4d5 and so forth. Just basically what you should be aware of is that sometimes electron promotion occurs to increase stability. That's basically it, which is an explanation to what we would expect electron configuration to look like versus what experimentally it's determined to be. Yeah. Most of the time it moves 1, but like in this last one it moved 2, and it's actually because, yet again, you can put 1 electron there to make 9, leaving 1 in the s, but D orbitals are much larger, so even if you put 2 in there, they're still much more spread out than a s orbital would be. Most of the time just go with 1. Okay? Alright. And moving on. So that's electron configuration. Oh, regarding electron configuration, you're supposed to be able to determine if something's paramagnetic or diamagnetic. Paramagnetic, I just remember paramagnetic, parapolar. If I think polar, I think has the ability to attract to another polar region or another area that's mismatched in its distribution of charge. So polar or paramagnetic means that you have unpaired electrons, meaning there's no cancellation of magnetic force. Because the electrons are spinning, right? So they're creating a magnetic force. So if you don't cancel out that magnetic force, it's going to respond to a magnet. So give me something that would respond to a magnetic force. Copper, okay, it's slightly polar.
Iron.
Iron, yes, because as you guys look over there, I'm just going to point over here. How is D block filled here? What's the orbital diagram look like?
It's 5 orbitals.
5 orbitals with
3 and with 3 other orbitals.
with what?
Well,
5 orbitals with what? 1, 1, 1, 1, 1. Are those paired? No. So does this exhibit a magnetic force?
Yes.
Certainly, because everything's spinning up, so it's creating a force of a magnetic field around itself. So it will respond to a magnet. That's why iron is magnetic, right? You can pick it up with a magnet. So what's not magnetic? Say again? Zinc. What else? Cadmium, go right down the line, right? Mercury, copernicium, anything that's got a 100% filled orbital system will have all cancellation of every single magnetic force it's created, which means it should not act upon a magnet field or magnetic field. So I remember parapolar, diamagnetic just don't. They just don't. They just don't do anything. Okay, so that's how I remembered it for like 12 years. Okay, question?
So is it only metals that are magnetic?
No, gases can be magnetic too. It's just often we don't hold a magnet to a gas and see any result. But if you have like liquid oxygen, is oxygen magnetic or is oxygen paramagnetic or diamagnetic? Here, if you liquefy oxygen, it will respond to a magnetic force. Okay, we okay here? These are simply 2 definitions that you should be able to predict. Yeah.
So anything's paramagnetic if it's not in like the last block.
Yeah, so they're like far exceeds. There's most of these things over here are paramagnetic. There's only a couple things that are dia. Everything in group 2 is dia, meaning don't. Zinc's area here, group, and noble gases. Oh, and the end of F block here. They would be filled. That's what I'm saying. They would be, so they're not going to respond. Okay. So we just talked about this. Copper is slightly paramagnetic because of this lone electron that's not paired. Yep. Okay, excited state. So when you have an excited state, you haven't done anything truly to the electron count. You just taken, before I move on, everything we've written so far has been ground state, meaning it has the electrons closest to the nucleus possible, filled according to Aufbau's rules, in the stablest state they can be. So when you excite an electron, you're moving an electron from ground state up to an excited state, meaning an energy level farther away from the nucleus than it should be, which means that we write the electron configuration slightly different. All we do is pull one of the last electrons and throw it in upper energy level. That's it. Okay. So the electron configuration for let's not do hydrogen. Let's do hydrogen. 1s1. Okay, we're done. That's ground. Make it excited.
2s1.
2s1. And if it was like super excited, it could be 4s1. But really, you're just putting it in a higher energy level. Something a little bit more complex than that, though. Let's do nitrogen. 1s2. Ready when you are? 2p3, right? So the the second energy level is the last energy level. The p sublevel is the one that is of most energy currently. So I want to excite one of those in the p sublevel up to another energy level. So to make it excited, we go 1s2, 2s2, 2p2. I'm just going to take 1 and pop it where? To the 3s1. We're just going to put it up into a higher energy level than it should be at. So what you're noticing is that this is in order, according to Aufbau's diagram, this is in order. So this is what state? Ground state. And because we went out of order here, that should be indicating to you it's excited state, right? And it's not an electron promotion kind of thing because we're not dealing with transition metals. All right, so what are some ways we can excite electrons? Okay, shining really high energy light like UV light. So we can excite by like UV light. How else? Come on, Megan. Megan. putting them in fire, okay?
Wow.
And what's another way to so I have some lamps back there. When I turn the lamps on, there's gases inside of that lamp that light up. Thank you, electricity. Okay. Just trying to see what you know. Okay. You can electrocute them, you can set them on fire, or you can shine high energy light on them. Wonderful. That is how you excite electrons.
It's electrocuted electron.
All right, back to me. So if another version of writing electron configurations is to not write the ground state or the excited state, it's to write the ionic state. So like of an ion. So what's calcium's electron configuration go? All right, so that's straight up calcium, right? How many valence electrons does calcium have? 2. You know that from the periodic table, and you know that from here. Where are they at? At 4s. So when I form calcium 2 plus, what's happening to the electron configuration? So 4s2 gets gone. Okay, so this is losing 2 electrons, forming a cation. Why does it choose to lose 2 and not like 3, 4, 5, 6? It goes back to its last octet, right? So its last octet was 3s2, 3p6. So it's only going to lose enough or gain enough to achieve octet, which this now, 1s2, 2s2, blah, 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 all the way over here to 3p6, this looks like who? Looks like the electron configuration of argon. It is the electron configuration of argon. So it's not argon. Like, we didn't just change calcium to argon, because what did we not change? Proton. Proton count is identity. If we don't change protons, we're not changing the identity. So it's stopping at the electron configuration of argon, because argon has octet, argon is stable, everyone's be like the cool kids, the noble gases. Another thing to think about is the terminology used in AP that we didn't use in honors. The word is isoelectric. Iso means what? Same, like isosceles triangle, 2 are the same sides, right? Like isotonic solution, same molarity inside and out. Isoelectric means same. Electron configuration. I'll put those together for you guys. Okay, so calcium, argon. Who else has the same? Calcium 2 plus. Sorry, argon. And give me one more that's isoelectric with that.
Potassium chloride.
Chlorine 1 minus. Keep going. Who else? Potassium 1 plus. That's good. Okay, so basically anything that backs up to argon is isoelectric with argon. All right, I'm moving past this. Ready? Okay. Oh, have you memorized the order of the electromagnetic spectrum? Gonna X, your voice, in my radio. That's an acronym that stands for gamma is what? Gamma, X, X-ray, your, like your voice, V, visible, gonna X your voice, in my, what's my? What's microwaves? Oh, hon, yeah. Infrared. Oh no, gonna X your voice. Oh, that's supposed to be over here. In my radio. Okay, so who's the shortest of all the wavelengths here? Gamma. Who's the highest energy? Gamma. Who has the highest frequency? Gamma. So now you know the relationships. Long, slow waves have low energy and explode. Right? Really high frequency waves move really, really fast and they have short wavelengths. Got it? Okay, so you should know the general order, general wavelength versus frequency versus energy. So that's all qualitative, of course, right? We're going to calculate this now. Calculate with these equations. So the equation that you are more aware of than this one is C is equal to lambda times frequency. C stands for speed of light, which is
3 times 10 to the 8 meters per second.
meters per second. So it's like a speed, like you travel to school at 30 miles an hour. So it's a distance per time. So speed of light is meters per second. So most of the time, I will give you wavelength in nanometers because I'm just a horrible person. but you cannot plug nanometers in here because if C is meters per second, what should this be recorded as? Meters. It's a wavelength, right? Length is meters. And then V, which means frequency, should be recorded as per second. So that's 1/seconds, right? So that in the end, everything shows equivalent units. So as a reminder, if I give you 400 nanometers, you must convert those nanometers to meters. If you don't remember how King Henry died, let's review that real fast. King Henry died drinking chocolate milk, ... nano, which is like a U thing, ... Hold on, did you say micro? Did you just say nano? I think I repeated what you said, but I don't know what you said.
You said nano.
That's micro, sorry. So, so you got mega on that side. Those dots matter. So when I say ... it's not just like me just leaving spaces. Those are placeholders. They have a unit or a prefix, but nobody really cares what they're called. So mega ... King Henry died by drinking chocolate milk ... Micro ... Nano ... pico. Okay, and then like femto and something else. So essentially, how many nanometers are in a meter? Can you give me a number?
10 to the 7. 10 to the 7.
You skip the zeros. I mean, you skip the spaces somehow. So you put the 1 at the bigger unit. Meter or nano? Who's the bigger unit? Meter, right? So 1 meter as that base, because meter is base, not milli. Meter is base. So 1 meter contains 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. How many zeros? 9. I'm not writing a billion. 10 to the 9th nanometers it is. Nano 9. You can't mess it up, okay? So 400 divided by 10 to the 9th is 4 times 10 to the -7th meters, and that would be a more appropriate wavelength to plug into our speed of light equation. Okay, so like I said, I would likely give you nanometers. You have to convert, but it's just moving the decimal back 9 places. Okay, so everything that is in the electromagnetic spectrum moves at the speed of light. Check. Okay, what's really important here? Energy of a photon is directly related to frequency. Fast things have high energy. Slow things have low energy. Okay, fast things have what wavelength? Short, and then slow things have long wavelength. So you should know the correlations. This does correlate back to the mass defect from from Einstein's equation E=mc². Normally we say mass is not destroyed or created in reactions, right? Law of conservation of matter. But like in nuclear decay or nuclear bombs, atomic bombs, we have a ton of energy being produced out of nowhere. But it's actually from a small amount of mass that is converted to energy. It's not destroyed. It's just converted to energy, which is normally what we never would say, ever would say in honors chem. But it's true. Okay? And then, so the relationship that we spoke of here has its own equation. E is equal to hv. What's h? Planck's constant, which is
6.626.
ooh, reference table. Is this on your reference table? It should be at the top left. Do not look at the honors chem reference table. Not that one. Yes, okay. So AP Chem has different stuff. Honors doesn't get that, okay? So Planck's constant helps us to understand the energy in one photon, one packet of light. Okay, so one photon. So E is equal to hv is actually E of photon equals hv. If I had a mole of photons, well, how would I get to the energy of a mole of photons? Multiply by. We haven't used this in a good hot second. 6.02 times 10 to the 23rd photons. Okay, so if I wanted to get to a mole of photons, I would take the energy I achieved from one photon and I'd multiply by Avogadro's constant to get to a mole. Cool? All right, I say that because you have a homework problem related to that. And you're like, oh my God, I forgot what a mole is. Okay. I'm going to skip to Berkeley for a second, but I do want to show you before I move on. So we know this relationship now. We know C is equal to lambda times frequency, and we know E is equal to Planck's constant times frequency. What's the common variable here? Frequency. I want you to set these equal to each other and figure out a relationship. solve for energy. Okay, I want a new formula for energy. Go. You can math. Hardcore. We just have a little bit more. Promise. Yeah, I don't. If I can avoid using two equations, I avoid using two equations.
You're thinking we're both now. HC over V are going to install.
Right, when you solve for V for this equation, what do you get? V is equal to C over lambda. When you solve for V over here, what do you get? E over H, right? So this is equal to this, so I can set these equal to each other, which means C over lambda is equal to E over H. Solve for E. C times H over lambda. Okay, so you can solve for energy given wavelength, when normally you cannot solve for energy given wavelength because they're in two different equations. Now they're in one equation. Or if you had to solve for wavelength, how would you solve for wavelength using this equation? Wavelength equal to, you just replace these, right? You just flip it. Right. So that's a way to converge the equations so you're not working too hard, but of course that equation is not provided to you. You have to derive it yourself. Can I move on? Okay. So I'm skipping to Bernoulli for a second. It's not that he's not important, but you can read about particle wave duality. Photoelectric effect is simply a method of exciting electrons using photons, photoelectric light electrons. That's how you break that word down. So essentially you can shine light on a lot of times metals, simply because metals have loose electrons. Remember those C of delocalized electrons for metals? Some of you are like, yeah. Okay, so C of delocalized electrons just means that electrons are really loosely held in metals. So if you shine a light on it, it pops an electron out, which essentially means that particles like electrons can have light properties, meaning wave-like properties, meaning they can have a wavelength or they can be affected by light. So it's also related to the particle wave duality. We actually talk about this a lot more in our PES, photoelectron spectroscopy part of this unit. So really it's more of an introduction and then we'll talk about it more. That's really all I'm going to tell you there. Wonderful. This is where you guys got to. This first introduction, this one right here, what is this like black one with the bright lines called? A bright line emission spectrum. We don't, it's no question. It has bright lines on it on a black background. It's called a bright line emission spectrum. Those emissions are coming from electrons going from their wet state to wet state, excited to ground, right? So we have to excite the electrons first and then they fall. And so every atom has a different number of electrons, which has a different number of electrons that can move and be excited to various levels, and then they fall in different methods, giving us different numbers of bright lines. You can probably see on hydrogen it's just a few, but barium has a bunch, and so that's called an atomic fingerprint, simply because just like humans, everybody supposedly has not fingers, fingerprints, different fingerprints. Therefore, they call it the atomic fingerprint because supposedly every element has a different number of bright line or different variation of its bright line spectrum. So you can now, in red right here, you guys write that part down, you know why these bright lines are forming. One thing to note, though, that's the equation I had you guys just write down, obviously. It's the same, we just wrote down. But it's because these electrons transitions are only, there's only a certain energy transition that can occur. So it's very predictable. If you go from n equals 4 to n equals 2, you're going to release a certain amount of energy. If you go from n equals 3 to n equals 1, you're going to release a certain amount of energy. So it's very predictable because of this quantized, meaning set amount of energy per energy level. And that's what we're going to calculate. Give me a thumbs up when you're good. If you release a lot of energy, oh, I didn't do this for you. You guys might know this though. UV stands for ultraviolet. So the visible spectrum sits right next to that, right? Visible spectrum, rho G, which part of the visible spectrum sits next to UV? Violet, right? Ultraviolet, on that side of violet. What sits on the IR side? What does IR stand for? Infrared. What color sits next to it? Red. Now, so some of you guys are like, did not know that, but that's how you know how the colors are arranged. So which was higher energy, UV or IR? UV. So which is the highest energy form of color? Violet, right? Purple. So essentially, bigger drop in energy should yield, if it's going to be in the visible spectrum, should yield what color? Say again? Purple, right? And a smaller drop in energy should correlate with red, or you of course have a range in between. So this is what our lab is going to be related to. We have a gas that will excite with electricity, so I will electrocute it. You look through a small slit in a spectroscope. It will be passed through a diffraction grating, like a prism. I know CJ said great colors. Okay, so so we're going to see that path be diffracted in different ways, and then we'll see the bright line spectrum. Somebody will hold your hand. Just okay. All right. Every single year I have somebody who's colorblind, and I'm holding. All right, so that wasn't a burn. That was just an awareness activity. Okay. So read this, and then tell me what else you need to know. I kind of just explained this. So I just explained the energy proportionality to the distance dropped, which is correlated to different colors. Now, it does say Bohr's model of hydrogen, because it's really truly only true for hydrogen. Hence why the quantum mechanical model exists, because they were like, well, there's 109 other elements to discuss. So the quantum mechanical model fixed some of the omissions that the Bohr model was able to explain. Science, we had to come up with more ways to explain everything we see. Okay. So this is what you have to memorize, okay? But I have a way for you. Do you see all of the drops from n equals whatever to n equals 1? They're called the Lyman series. I have this bigger down here, just wait. And then all the drops from whatever to n equals 2 is called the Balmer series. And all energy level drops down to n equals 3 is called the Paschen series. You have to know the series names and what they correlate with. Marcus, you getting it together? Good? Okay. So every drop that's in the Lyman series drops from wherever it is to the lowest energy level of n equals 1. So remember that drop. Remember I told you that n equals 2 and 1 has the biggest energy level difference? So that's relevant now, because a really big energy level difference means that you release the most energy. And if you release the most energy, we're going to consider that UV likely. Okay, so Lyman low, and that's going to be releasing the most amount of energy because of that nature of the drop. Niall, get up and stand up, son. Go stand up at the lab station. Balmer, I remember Balmer drops, like Balmer to me, I think B2 by 2. I'm just trying here, I'm stretching. But Balmer by, and it's going to drop to the second energy level, which is releasing a mediocre amount of energy, which that's kind of like smack dab in the middle of the EMS, which is visible light. And then Paschen, which is the one that doesn't drop that much, it only drops to the third energy level. Paschen, do you remember your organic? Remember Prop? Prop means 3. Do you remember that? Like propanol?
Yes.
I remember Paschen. Prop means it's dropping to the third energy level. And since it's not releasing a ton of energy in that drop, it's on the other side of light, visible light. So therefore it's this IR form of energy. If you're still writing, right, close your eyes. Lyman releases what type of energy? Close your eyes. No, Lyman releases what type of energy?
High energy.
Which is ultraviolet, right? The highest form of energy in this. And then Balmer releases what type of energy? Medium, which is visible. And then Paschen releases the lowest form of energy, which is infrared. Okay. So you do have to memorize those. But I've tried to give you hints. Lyman low, Balmer by, Paschen Prop. I tried. If you can write something better, you just let me know. Just give me a thumbs up when you're good with that. Okay. Great. Okay. So back to like what these transitions are representing. We know they're representing a set amount of energy, which is correlating to a set wavelength. So that set amount of energy is going to have a calculation now, and it's using the Rydberg equation or the Rydberg formula. And this is not it. So just don't write this down yet. Hold on. So I don't believe, is this on your reference table? It used to be, and then I believe they took it off.
No.
Something with like an R. I mean, not just any R. RH. Okay. Well, here we go. So essentially, each energy level has a set amount of energy, which is calculated by the Rydberg constant, which is 2.187 or 78 times 10 to the negative 18th joules. And what you do is you take that constant discovered by Mr. Rydberg, and you multiply it by this ratio, where the ratio is the atomic number, which this whole entire thing we're doing right now is just Bohr model, Bohr. So what atom are we speaking of?
Hydrogen.
Hydrogen. So the atomic number for hydrogen is 1. So when you plug a 1 in there, 1 squared, you also insert the energy level you're speaking of. So if you're talking about energy level 3, which is the energy level, you plug a 3 into the N right here. So from that equation, using this constant and this ratio, you can figure out how much energy is in a given energy level. Who has the most energy? Energy of like level 1 or energy level 6? Energy level 6. The farther away you are from the mama nucleus, the crazier the electrons are. They have a lot of energy. The closer you are to mama nucleus, you're a really good person. You are yes ma'am, no ma'am, you have low energy. Okay, so that n equals 1 is not going to have a lot of energy. So we don't calculate just straight up the energy up in energy level. We're more concerned about the transition, like when the electron drops from 6 to 1. How much energy is released? So we're going to say a lot, right? But we want to calculate. So here's that equation. I'm going to make sure it's written clearly here. Just hold off to that for a second. It's down here at the bottom. Okay, here. So it's negative, so write this down for yourself, right? Energy, I'll write it with you guys so it's a little clearer. Energy of a photon, which is coming from a transition in the Bohr model, is equal to negative 2.178 times 10 to the negative 18th joules times parentheses 1 squared over n final squared minus 1 squared over n initial squared, parentheses. So we have a final and initial, right? Remember, that's always how we calculate things, like for temperature change, final mass initial, energy final mass initial. We do the same thing here. So if I'm going from n equals 6 to n equals 1, first off, you tell me, is energy being absorbed or released through this process? So we're going from a high, I heard two different answers. Let's say this is n equals 6. If you're going from n equals 6 all the way down to n equals 1, you're going from an excited state to a ground state. So what happens? Energy is released. If energy is released, you will end up with a negative number, which is hence why this negative is set out front to achieve that with this subtraction process. So if it's released, you're going to have a negative number. We don't always have to record energy as negative. It's just note that when it's negative, you're saying it's released. So if I was going the opposite way from 1 to 6, what would you expect? Same number but positive, right? So it would be an absorption process. Can you see absorption of energy? No, right? You can only see the release of energy. All right, this is called the what equation? Rydberg, right? Rydberg. Okay. And that's the energy of one photon, right? So if you had to go to an energy of a mole of those same photons, multiply by Avogadro's number, right? Okay, can I go past this? Oh, good, that's my timer for other people. All right, calculate the energy released from n equals 5 to 1. I'm going to go grab these people. And then you guys can figure out the wavelengths in that process. So show your work for yourself. So when you have homework on this and you don't have an example, don't text me. Don't FaceTime me.
Are you doing this?
But you know, why don't go back and watch some of the videos if you turn it down?
So, that's tools. Yeah. Gauge is a constant. It's 1 minus 1 multiply that we have negative. Negative 2 points.
Six minus something equal 1 and 5. Yeah.
Wait, so this went from 5 to 1 squared.
Yeah, release is positive, release is negative.
All right, what do we have? Negative 2 times 10 to the negative 18th energy unit. Joules, right? These didn't have units, so this is the only unit here. Guys, you can drop that on my desk right here. Okay, don't put the box. It's there. All right, so now that you know the energy, you can correlate that to the. Oh no, don't give me the moles. Give me to wavelength. Okay, I want to get to wavelength of that. So if this is the energy, what is the energy wavelength equation? E is equal to C times H over wavelength. Okay, so I don't really like the way that's written now because it's solving for energy. Solve it for wavelength for me. Switch the E and the wavelength. So wavelength is equal to C times H over E. Okay, what's C? To the 8th. I know, you got to remember who's negative. Remember, speed of light's super fast, so it's going to be a positive 8. That's meters per second times what?
6.6
Times 10 to the
negative 34.
negative 34 units on that one? Joule seconds, right? It's joules times seconds. All of that over that. Do I put the negative here?
Yes.
Yay or nay?
Yes.
No. Net wavelength can't be negative. You cannot have a negative length. Okay? So we don't put the negative because remember the negative is just telling us what? Right, you're jumping from 5 to 1, you better be releasing energy. I know you express the energy as negative, but we do not express it down here as negative. This is 2.09 times 10 to the negative 18. Put this in your calculator correctly. Parentheses, 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 parentheses. I can't see. What is it?
I'm not sure it's right.
Is it to the negative 7th or negative 6th or something?
Negative
I'm good with that, yeah.
9.507.
So 9.507 times 10 to the negative 8, what? It's wavelength, what unit?
Meters.
Meters. And then we're going to talk about how that cancels here. So this is meters per second, this is joules times seconds, and this is joules. What cancels? Joules on top, joules on bottom, and this is seconds on top. I know it's low because I ran out of space. So seconds on top, that's seconds on bottom, leaving me only with meters. Yay! Yay. Okay. All right. So can you estimate? Okay. Let me just tell you this first. Wavelengths for visible light are from 400 nanometers to about 700 nanometers, which that's 4 times 10 to the negative 7. Okay. So light or visible light is from 4 times 10 to the negative 7 meters to 7 times 10 to the negative 7 meters. Where does this fall? Is that bigger or smaller than visible light? Smaller. So where would that potentially lie? Near ultraviolet. Yay! Good job. Okay. Yay! All right, we basically covered all of Honors Chem Unit 2, the first half. Okay, so I'm going past this. Are you guys almost good? Okay, so Rydberg equation. Write down what you need to. Rydberg equation is useful for finding what? The energy of a photon, keep in mind, in what situation, what scenario?
Dropping level.
When it's dropping or raising, right? In the what model? Bohr model. This is only true for hydrogen. Okay. I think I'm going to stop now. Yes. Okay. So, meet me in the lab. Bring your packet, the packet that you got yesterday. If you weren't here yesterday, here's your packet. We have 27 minutes. Like, we'll do a little bit and we'll do a little bit more later. I knew I had to get you content before you do this. Color stuff, yeah. No. We'll do the flame test on Monday. We're doing spectroscope lab first. We can't do flame test until we do spectroscope. I don't necessarily. It's a habit. You know, you grab your
I was like, spectroscope.
Maybe that's good. Go to the lab station. Hi, go to the lab station. Talk. Five, four, three, two, one. Okay. So let me quickly tell you what you're doing. Turn to the second to last page in your packet. Maybe not the foldable one. One before. One more before. So fourth to last page. Fifth to last page. Fifth to last page it is. Do you see spectroscope or do you see hydrogen emission lab? Okay, so I'm dumbing this down real hard, right? Okay, so we have a hydrogen discharge tube right here. I'm going to lay that's only a few you can see the time, so that's why you should be patient. You're going to point it at the spectroscope at this light, but everybody look up at a spectroscope if you have one nearby. Hold it with a slit on your right-hand side and the diffraction grating on the left-hand side. So the little slit is in the front, it's on the right-hand side, and the diffraction grating is on the left-hand side. Look over the light, and then you see a number scale. Like it starts with 7 and it reads to the right down to like 4. Yeah. Okay. Those numbers are big fat lies. Those don't mean much at all. Okay. So as you can see in the reading here, it says the number on the spectroscope you must multiply that by 1,000 to get to angstroms. Do you remember the A is the halo? Angstroms. So an A of the halo is a form of wavelength, but it tells you in here the relationship. 1 times 10 to the 10th angstroms, so like a little over a billion, right? So 10 billion. That's equal to 1 meter. So who's the bigger unit? The meter or the angstrom? Who's the bigger unit? The meter or the angstrom? Meter by far, right? There's like 10 billion angstroms in 1 meter. Got it? Okay, I know. It's describing. So at this point, I'm going to give you data, and then you guys need to read through the lab to see what calculations get to be achieved. So I'm going to just call maybe 5 or 6 of you guys at a time while I electrocute this guy. All right, I need, you guys can send me one person to come back and deliver information. Okay, so I need like 5 people.
Wait.
All right, next 5. If you need something, let me know. Okay, so all right, everybody should have seen what they need to see. Do you have data on your data?
I got a 7.
No, this is a line. Are you on your line?
Yeah.
I saw one color. Sorry, my eyes are.
And then one year,
All right, guys, just listen up from the board, or look at the board for me. 3, 2, 1. Eyes, not spectroscopes. All right, so you have 4 lines. I actually don't know why this is 5. I'm sorry. So you had 4 lines. You probably only saw 3. So I want you to take, what was it? Red, turquoise, violet, violet blue. Red, turquoise, violet blue. You have an observation of a angstrom reading you have. You need to go ahead and take that to wavelength in nanometers. And then I will tell you I'll tell you the accepted nanometer. The calculated nanometer is using the Rydberg equation. Okay, it gives you a version of the Rydberg equation up here. It's a little different than what we just spoke of, but I prefer the energy one down here and then converting energy to wavelength. I think it's easier than using that one. All right, so go. You have 3 to 4 calculations to do right now. You have a packet, right, Emily?
What's that one
Yeah, eventually.
Sweet.
All right, kids, here's your accepted values. Violet, like the real violet, not the blue violet, 410.0. The blue violet, 43 or 434.0. The blue green, the turquoise one, 486.1 nanometers. And then the red, 656.2 nanometers. Okay, so those are your third or fourth column, whichever the last column is. So I am not going to have you do you see where it says analysis questions? Scratch, I'm not going to have you do those because I didn't get to do the homework last night to practice light because we weren't there. So I'm just going to scrap those and have you do the stuff instead that I was going to have you do yesterday. So, but do you see questions 1 through 7? You're kind of like, what, are you on question 3 or 4 right now, which is the calculation phase? Well, but if you look in the table's like right under question, what? 3. So the rest of those questions are asking a little bit about energy, emission spectrum, and then absorption spectrum, emissions. You have to draw a little diagram, put some colors on it. So that's a good wrap up to light, okay? And then open your packet to the first page and circle these textbook numbers. You see that copy, it looks like a textbook, I've copied it. It's because I really liked those questions from the first textbook I used for this class. And those are questions 39, it goes in order, okay? Question 39, 40, those first 2 are easy, like single step ones, okay? 45, 52, and 55. So essentially the first 5 questions there, yeah? Okay. All right, so that's going to basically finish you out on light. We won't deal with light much more next week. Okay, so I told you the first part of this goes pretty fast because it's a lot of prior knowledge. So you have a couple more minutes if you want to chat with me or look at your, talk to me next to you. Finish up some more of those analysis questions before you go. So do not pack up yet. You still have 3 more minutes. Do something productive with your lives. Okay?
So what's on the AIDS?
Huh?
What's the
Mega? We just went over
No,
that.
megahertz. It's like,
So megahertz is just mega, and it's just a form of, it's a, hertz is a base unit. Anytime you have a prefix, start from base and figure out the prefix
how do you
exists.
get wavelength from?
Hertz is the same thing as frequency. So frequency, sorry, I did not mention that. Frequency comes in 3 flavors, 1 over seconds, 6 to the -1, and hertz.
Just
They all mean the same thing. Yeah.
megahertz.
So do you know how to get from mega to base? Okay.
Do you know possibly what you're doing with your science section? You just all the
I can let you know later. I have a calendar, and it's pretty much in place. I'll let you know. Okay.
Where should I look for my earphones?
So,
I'm probably lost.
hey, probably you were absent one day.
I wasn't worried about it.
In the box. It was nice and nice here. Checked over them and talked to them. I'm going to look at it later. So you might want to use it.
Is it cool if I come back in intervention? I have one question on the test.
I've got blah 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 blah. Homeroom,
Okay,
so
cool.
it should be alright. Okay. Hey.
Do you need me to finish the procedure?
Yeah. So you're just finishing these questions correlating in the procedure.
Okay.
You're not doing
You don't have to
these.
do this number 4.
Well, no, do that.
Okay.
Yeah, 1 through 7.
Okay.